Hi guys, welcome back to Data Every Day. Today we're looking at a dataset. It's actually a soft drink dataset. I know there's not a lot of annotation on this dataset description. It does say hiring competition dataset, so maybe this is a dataset used for some sort of hiring competition. But essentially, what's going on here is um, we have different shops and different brands of cola or soft drink, and then different containers that they're stored in, which contain different capacities. And then at the end here, if we see all the columns, you can see we have the price and quantity sold. And we're going to try to predict the quantity, which is the recommended target variable here. We also have the city that it comes from, latitude, longitude, population of the area, and like I said, the shop. So we're going to try to make predictions on the quantity using the other features. So let's hop into the notebook. I'm going to import NumPy and pandas just for working with the data, and we'll only be using the train test split function and standard scalar from sklearn for preprocessing. And then these are all the models we're going to use. It's a good variety of models, so we'll see which one works the best. So I'll go ahead and import all of that, and if we look at the CSV files, we have actually the test set has already been taken out for us. So we're going to try to process both of these, probably using the same function. So I'd like to import them both into the environment here using pandas.readcsv. I'm going to call the train set traindf. So that's pandas.readcsv, and I'll pass in the file path for the train set. And then we have testdf, which will be pandas.readcsv, but passing in the file path for the test set. Now let's take a look at both of them. So here is traindf. We have 7,500 rows and 12 columns. And here is testdf. We have about 1,000 rows and also 12 columns. So let's get a little more information on traindf. So we can type .info. And you can see we have some missing values here. I mean, we can also see that here. So we're going to have to take care of some amount of missing values. We also should note that we have some blank rows, completely missing rows. So these are rows that are actually useless to the data set. We can just drop all those. So we'll employ some methods to automatically remove them. And then we notice we also have 6 object columns. So these are I don't know if date is considered object. Yeah, okay, date, city, shop, brand, container, and capacity. And then all the rest is numeric. So we'll have to encode these object columns appropriately. Now let's take a look at some info here. It should be roughly the same. We do have some missing values going on. So yeah, also 6 object columns. So let's get into it. Let's start preprocessing. So for preprocessing, I'm going to create one function called preprocessInputs. It's going to take in a data frame. It's going to make a copy of the data frame, and then it's going to return that same data frame. So right now, all this function does is make a copy of it. But now we can create 2 new sets of the data. We'll call them xtrain and xtest, which will be the processed versions of traindf and testdf, respectively. So we can call preprocessInputs on traindf, and then down here we can call preprocessInputs on testdf. And now down here, xtrain and xtest are going to be the processed versions of traindf and testdf. Alright, so the first thing I'd like to do is actually drop this ID column. So the ID column is a unique identifier for each example, so therefore it's not actually providing any information that would be useful in predicting the quantity. So let's go in here and drop ID column. So we can do that with df.drop. ID is the name of the column, and we're dropping from axis 1, which is the column axis. So now you'll see we run this on both the traindf and testdf, and we'll have dropped them from both xtrain and xtest. So currently xtrain and xtest contains our target as well. At the end, we're going to split the target off and store that in ytrain and ytest. So next thing I'd like to do is remove these missing rows. So there's probably a few ways to do this. What I'd like to do is use the isNA matrix, xtrain.isNA, which gives us a true in a given location if there is a missing value there. So you see all the missing values match up to trues, and all the others will match to false. So we can actually ask a question about this. When we have true falses, we can call .all. And that .all is like a Boolean operator that checks if all the entries in a given list, series, or some array-like structure are true. So if all of them are true, we'll return true, and if all of them are false, we'll return false. And in here, we want to specify an axis along which we're checking. So by default, it's 0, and that will check along axis 0, so the row axis. And if all the values in a given row are true, then we'll get a true. And you can see that's obviously false because we can see there's at least one, well, in here. Let me look at the isNA actually. xtrain.isNA. We're doing it along axis 0 here, so we know there's at least one false in every column, so we're going to get false in every column. But if we change this to axis 1, we'll actually get, we'll be checking across axis 1. So we'll be checking if all the values across a row are true, and we know we'll get some trues for that. So here are the rows that have all missing values in every entry, and we can count up how many we have by summing. So there are 1,080 different rows that have no information. So we're going to drop all of those. And so the way to do that, we can actually use this true-false series here as an indexer in xtrain. So if we call xtrain and then index like this, we can type .loc and pass in this as the row indexer and then all columns. That will return just the columns that have full missing value rows. Sorry, not all the columns. All the examples, all the rows that are just missing values. And then we can get the index of this .index to return the indices that we'd like to drop. So in here, I'd like to take this, put it into our preprocess function, say remove missing rows, and I'll call this missing rows. Missing rows will be the indices of each row that's missing. And all I have to do here is change xtrain to df. All right. And then all we have to do in here is say df equals df.drop missing rows from axis 0 this time. And whenever we drop rows, unless there's a reason to save the indices the way they are, we will want to reset the indices. So we'll call reset index and include drop equals true to prevent the old indices from becoming a new column. So let's run that. And now we can see those rows at the bottom are gone. If we check the isNA, let's now sum over just sum this thing over the columns. Sorry, over the rows, so that we'll get the total number of missing values in each column. And now this is more reasonable. These are the actual missing values that are not contained in those fully missing rows. So these ones we can actually manage on a case-by-case basis. So let's see. We want to try to figure out what kind of data types are in each of these columns that have missing values. So latitude and longitude, these are both numeric columns, and we can usually fix this by filling in the latitude and longitude with the mean. It is a bit of fabricated data, you could say, but it usually works. It works pretty well by filling in the missing values with the mean of the column. Then for container and capacity, which are the other two with missing values, we should actually check this for xtest as well. xtest.isNA.sum. We have this here: latitude, longitude, container, and capacity. So we have the same columns that have missing values in both the train and test set. So we can just handle those explicitly in our preprocess inputs function. Right, so the container and capacity, these are object columns, so we can't just fill them with the mean. You can't calculate a mean from a bunch of strings. However, you can use mode. And this is a sort of preference. You can definitely test out which works best, but you want to check what kind of encoding scheme you're going to use when filling these in. So, for example, with one-hot encoding. One-hot encoding is best for when there's no ordering between the categorical values. You can do that with pandas.getDummies. And you pass in the column. So we would one-hot encode this container column because there's no ordering between the values in there. And that will send each unique value to its own column, and we'd get a vector that represents the original value that we had. So this one was glass, so now we have a 1 for glass and zeros for all the others. And this is a nice way to encode categorical variables that have no ordering between the values. However, this also takes care of missing values. And what I mean by that is if there's a missing value in one of these spots, we'll just have all zeros across. There will be no 1 present. And so some people like to also add their own little column for missing values to specify that there was a missing value there, which is doable as well. All you'd have to do is fill in the missing value here with some other string, and then that will show up as its own dummy column. Additionally, you can just leave it off because we just have all zeros. And the third option is you can fill it in with the mode if you want. So I guess we'll just not deal with it. We'll just one-hot encode it and allow the one-hot encoding to take care of the missing values itself. But if you really are interested in optimizing performance as much as possible, I would recommend trying out all approaches and seeing which works the best. Alright, so let's go in here. And we'll start by filling the numeric missing values, which are the latitude and longitude columns, with the column means. So for column in list containing lat and long, so for each column, latitude and longitude, we're going to take the column and call fill_na on it, and this function will fill the column with, it will fill all the missing values in the column with whichever value we specify here, and I'm going to specify df subcolumn dot mean. So we take the mean of the column and fill in the missing values with it. And I'm going to store that in the column after we're done. Alright, so now if I run this, we take a look, and we look at the sum of missing values, you can see we no longer have missing values for latitude and longitude. So the only ones left are container and capacity. So like I said, for container, since we're going to one-hot encode it, we're not going to worry about filling in the missing values. But for capacity, it's a little different. And the reason is there is an ordering between these values. So this is what you call an ordinal feature. It's a categorical feature, but there is an order between the values. And so one way to encode this is to just set each one to an integer just in the right order. So we can look at the unique values in here, taking the capacity column and then typing .unique, and you can see we have 330 milliliters, 500 milliliters, and 1.5 liters. And that does progress in quantity. So I would like to order this and then encode as integers in the right order. So the way we can do this is by creating a list containing all the values. We don't actually have, oh yeah, we do have missing values, but we'll fill them later. Actually, we can fill them first. We can say fill ordinal missing values with mode. And we use the mode here because you can calculate the mode from a categorical column. You just can't calculate the mean. So we can get that if we look at xtrain dot subcapacity dot mode. It is 1.5 liters is the most frequently occurring example or value. And you'll notice this is in the form of a pandas series, so to harness the actual value we're going to want to index it at 0, and that will give us the string. So this is what we're going to fill up here. So we're only doing this for one column, which is the capacity column. So I'm taking capacity, and I'm setting it equal to itself with fill_na, and here instead of passing in the mean, I'm going to pass in the mode, and then I'm indexing at 0 to get the string. And now if we run this and take a look at the missing values, you see we no longer have missing values in the capacity column. So now what I was saying before about this ordering, if we check this now, there's no more missing values. We just have these 3 values in there, and we can order it like this. We take 330 first because that's the least, then we have 500 milliliters, and then we have 1.5 liters at the end. And so this is a proper ordering of the values in the column. We can now index this list with one of these values, let's say 500 milliliters. If we pass that in and index, we can ask where in the list does it show up, and you can see we get a 1. So that's because this is 0, 1, and 2. And so if we do this for every example, we'll actually be mapping a value to its index. And this is a way of ordinal encoding, right? You send a value to its place in the ordering, and by the end of that you have a column that just has numeric values. So I'm going to create, I guess actually, yeah, let's do it like this. So I'll say ordinal encode, ordinal, well, actually just the capacity column. So I'll say ordinal encode capacity column. And then I'm going to say capacity ordering. Looks like this. It's just this list that we created down here. So here's the ordering. And then what we do is we take the capacity column and we apply a lambda function to it that maps any x in the column. So that means any one of these is going to get mapped to capacity ordering dot index of x. So it will actually just index this ordering here that we specified with whatever the value is, and then get back the index or numerical version of it. So if we run this, you can see, oh, actually we didn't set it. We just have to make sure we set this column like that. And now you can see we now have 1s, 2s, and 0s instead of the original string values. And the ordering has remained intact. So the final type of encoding that we're using here is the one-hot encoding, which I showed you before with the dummies. I would like to note we can specify a prefix here on the end, which is basically, let's make it the same as column. That will just put this at the beginning so that we know where these values are originally coming from. It gives us this little indication of what column it originally came from. So what I'd like to do is make a separate function for this, call it one-hot-encode. And we're going to pass in the data frame, the column we'd like to encode, and a prefix we'd like to assign to each of these columns. So I'll start by creating a copy of the data frame so that we're not modifying in place. And I'm going to create some dummies. So this is using pandas.getDummies, just like before. This time we're getting the dummies for df sub column, and passing in the prefix of, now we could pass in separate prefixes for each one, but because these are pretty simple column names, I'm just going to leave the prefix in as the same as the column name. And then we're going to concatenate together using pandas.concat the original data frame and the new dummies we've just created side by side, so axis 1. And then when we're done, we'll drop the original column from which we created the dummies. Then we'll return df and we're good to go. So now down here, I'll actually do it here. One hot encode categorical features, or I'll say nominal features. Alright, so let's take a look at what we need to do here. So date is not a nominal feature. It's actually, what we're going to do with the date column is go in and extract the year, day. Actually, this is a day, month, and year. We're going to extract each one to its own column, and those will already be numeric, so we don't have to worry about that. So that is not a candidate for one-hot encoding. However, the city is. These values do not take any particular order, so they are nominal. This is a nominal variable. Then the shop, even though they're numbered 1 through 6, or however many there are in there, I would not consider this an ordinal column because there's no guarantee here that the shop 1 is less than shop 6. Like it doesn't really make sense. Even though they're uniquely identified by integers, they are independent shops. So I'm going to consider this as a nominal feature. And so far we have city and shop as candidates. And then brand is also nominal. There's no ordering between these values. Container also nominal. And that will sum it up. After that we just have numeric values. So we have city, shop, brand, and container. And so up here I'm going to say for column in city, shop, brand, and container. I'm going to call oneHotEncode. Remember, that's our function. It returns a data frame, so I'm storing it back in df. We're going to pass in df. The column will be column, and the prefix will also be column. Oh, I guess if we're doing that here, we don't have to specify the prefix here. So I'll just remove that part. I might as well just put this on one line. Alright, so this should do it for us for each one of these columns. Oh, and we missed a... Oh, I have to rerun this, okay. Alright, there we go. Alright, so here it is. You can see we now have all these one-hot columns attached to the end of our data frame, and all the original data is here. Note that the original nominal columns are now dropped, and we now have just one-hot encodings of them. So if we look back at this, you can see we now have no more missing values, and that's because the one-hot encoding did take care of the missing values in the nominal columns for us. So everything is in numeric form except for the date column. So last thing to do now is encode the dates, or I'll say extract date features. So I guess we can create our own function for this again. I'm going to call it encode dates. We'll take in a data frame, a column we'd like to encode, and that will be it. Again, we'll create a copy of the data frame just to be safe. And then I'd like to use the pandas.toDateTime function to process this. So let me just grab one of these examples. If we call pandas.toDateTime, and we paste in a string here, it will convert the string to a datetime object. And datetime objects are very nice because we can then call .year to get the year, .month to get the month, and so on. You get it. So what we can do is use these little attributes to give each value its own column. And so in here, we'd like to do this on a whole column. So first thing we'd like to do is call pandas.toDateTime on the whole column to convert the column into a datetime column. So df sub column equals pandas.toDateTime df sub column. And then we'd like to create 3 new columns: one for the day, one for the month, one for the year. So df sub, I can't just call this year because we'd have duplicates. Actually, that's not true. Because we only have one date, we don't actually have to do that. If we had multiple date columns, we would have to make sure that we specify which it is, maybe something like this, so that it each has its own name. But I think because we have one date, we'll be okay. I might even... Yeah, okay, I'll just leave it. I'll leave it like this. No, I'll just call it year. No, I'll keep it. This way, it allows us to generalize this function to other data sets as well. So df sub column year is going to be the original column, which has now been converted to a datetime column, with a lambda function applied to it that takes in a given x and returns back x.year. And because this is now a datetime object, we can just call year on it and store that in its own column called column year. Now we'll do the same thing down here once for month. So I'll change both of these to month. And then once for day, change both of these to day. And when we're done, we'll return df. So over here, df equals encode dates. And this takes in df and the date column. And we got a problem. Encode should be encode dates. Okay. All right. Oh, I forgot to remove the date column when we're done. So let's actually just put this at the end. df equals df.drop column axis 1. Okay. Here we go. So at the end here we have the year, date month, and date day columns, which were taken from the original date column, which is no longer here. So let's take a look at xtest now. Make sure that they're lining up together. So here's xtest, here's xtrain. They both have 28 columns, and they do seem to line up. So everything is going well. So the last thing to do is scale these. Actually, in our function, the last thing we're going to do is split the y off from the x. So y is generally the variable name used for the column you're trying to predict. In this case, it's quantity. So I'm going to split df into x and y. Y is going to be df sub quantity, just the quantity column. And x is going to be all the rest of the data. So we're dropping quantity from x, from df actually. We're dropping from axis 1. And then we're going to return x and y at the bottom. So now this returns two values, and over here I'd like to get back xtrain and ytrain for train df, and xtest and ytest for test df. And now you'll see xtrain no longer has the quantity variable, and that's being stored in ytrain. Xtest as well, and ytest as well. So looking pretty good. Last thing to do is scale the data, and we'll do this down here since we can't do that within our function. The reason being, I'd like to only fit the scalar to our train set, and we only get the train set after we've called this function. So down here I'll create the scalar. We'll use a standard scalar from sklearn. Now the reason to use a scalar is simply, well, if we look at, for example, xtrain.describe, you can see that the means and the standard deviations are very different for each column, and this can confuse some models, so it's very nice to standardize each column so that each column has the same mean and variance. That's one way of doing it. Another is min-max scaling, where you compress the values into a certain range based on the minimum and maximum of the column. But we're using standard scaling, which will set the means of each column to 0 and the variances or standard deviations of both columns to 1. I'm not saying that standard deviation is the same as variance. Standard deviation is the square root of variance, but when they're both when one is 1, the other is 1 as well. So scalar.fit xtrain. So we're fitting only to the train set because we want to sort of assume we don't have access to the test set. If we were given just the train set originally, which is generally what would happen in practice, you may not know what kind of test data will come later, so it doesn't make sense to fit the scalar to the test set. Test set is sort of supposed to be like unseen, even by you, while you're at the time of preprocessing. Alright, and then we'll transform xtrain and xtest using scalar.transform. So after the scalar's been fit to the train set, we'll transform both xtrain and xtest using that scalar and using that fit. And right now, these actually return NumPy arrays. You can see they have been scaled. We just can't see it very well because they're not in data frame form anymore. So let's go and turn these back into data frames with pandas.dataframe. And I'm just going to set I'll set the column names to be the same as xtrain.columns and xtest.columns. What's wrong here? No attribute columns. But I'm making a data frame. Oh, here. Oh, okay. Yeah, okay, I have to... Yeah, I have to run it only once on this notebook. We're going to get them back again, which will be data frames. And now when these are referenced, they'll still be data frames, so it should work. Okay. So here it is, after it's been scaled and it's back in data frame form. We can take one more look at the describe function here. And you'll see that the means are all extremely close to 0, and the standard deviations are all extremely close to 1. So the scaling has been completed, and now we're ready to train. So I guess let's bring this up. I'll just put it in the same block. Alright. Alright, so let's start training. We're going to use a bunch of different models today. They are these ones. So we have the k-nearest neighbors algorithm, which we'll start with. Then we'll use linear regression, both unregularized and then with L2 regularization. So that's what ridge regression is. Then we'll use support vector machines, one with a linear kernel and one with a radial basis function kernel. And then we'll use decision tree and a neural network. And then we'll use two ensemble methods. One is random forest regression, which basically creates a bunch of decision trees in parallel and then averages the predictions at the end, and the gradient boosting regressor, which creates decision trees in series. So let's run this. Actually, I already have run that. I just want to I'm going to create a dictionary of models down here. The reason I'm doing a dictionary is I'd like to associate a name with each instance of the model. And for the sake of time, I'm just going to paste this in. So I'm giving the name of the model and then the actual instance of it. So then down here I can call models models.items and iterate through it. So .items returns the key value pairs of a dictionary as tuples, so that we can do this. We can say for name and model in models.items. We can fit the model to start, and we're fitting on the train set, xtrain, ytrain, not test, train. And then we're going to print out just a confirmation message, so name plus trained, just to say that the model was trained. And then we can see that as each model trains, we can see a little status message that says it was trained. And then we can get the results down here. So while that's training, I'll do this. All we have to do is iterate again for name model in models.items. We're going to print out the name of the model followed by the r-squared score. So I'm going to display the r-squared score to 5 places and format it with model.score on the test set. So in the case of regression models, and these are all regression models, the model.score function will return the r-squared score. And r-squared is a great way of understanding how a regression model is doing. It basically measures the dispersion of the data around the fit. And we'll calculate the r-squared score on the test set and then plug that in here to 5 decimal places for a given model and for a given name. And we can see the results here. So it looks like we have some models that are doing well, some models that are not doing so well. The highest possible r-squared score you can get is 1.0, but that's nearly impossible to attain. And we can see it can actually go into the negatives if the fit is really bad. So here, the neural network, the support vector machine with a radial basis function kernel, and the support vector machine with a linear kernel all came up with negative r-squareds. So they're not doing so well. They're actually doing substantially worse than the other models. After that, it looks like we have linear regression, which is a fairly simple model. And that has an r-squared of 0.57. Then after that, looks like it's the k-nearest neighbors algorithm. These are also very simple methods. Then we start, well, decision tree, you might consider it simple, but it can usually capture more intricate patterns in the data than a simple linear regression. So we have a higher r-squared score here of 0.81, but the one that's really picking it up here, the two actually, are the ensemble methods, gradient boosting and random forest. We have 0.88 and 0.92 for random forest, which is the winner here. So if I was going to go and optimize a model here, I'd probably pick a random forest model and do my best to optimize the hyperparameters of that and try to get the maximum possible performance out of it. But yeah, so that was some of today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.